Greetings and welcome back. Today we'll be doing just a very quick recap of how to identify reactive sites. This will not be in great depth. That's all we've done over the last 2 days or so is to go into depth on this. So instead, this will just be a very surface level review of how to identify reactive sites given a structure. Let's start with nucleophiles and bases. I'll put nucleophile up here and base over here. And again, what we're going to be looking at here is strong bases and strong nucleophiles. Those are what I expect you to be able to identify on the quiz. So, in the middle, we have a lot of things that are both strong bases and strong nucleophiles. So, for example, any C- would be both, H- would be both, and N- would be both. And non-bulky O- would be both. All right, and those guys fit into the category of both being strong nucleophiles and strong bases. We have a couple things that are strong nucleophiles but not strong bases, and these are the halogens. So Cl-, Br-, and I- are strong nucleophiles but not strong bases. So let's put all of these together and say that these guys are our strong nukes. All right, quickly, a nucleophile is something that shares electrons with an electrophile. It is somebody that has too many electrons and wants to share them, therefore becoming more stable after it shares those electrons. So these are mostly negatively charged. Well, at this point, they are all negatively charged. The reason is after they share those electrons, they become neutral. So we have a couple strong bases that are not strong nucleophiles, and those are essentially just the bulky O-, or the bulky N-. All right, and so I will note up here that non-bulky N- can be both. All right, so when we're looking at what are the strong bases, we can group all of these guys up. There you go. All right, so if you see a molecule like this one, first off, what you should be looking for is the negative charge, which indicates that it is very desirous of sharing its electrons. It's something that, if it shares its electrons, can become neutral. I would say that there's a lot of bulk around that O-, and therefore this guy would probably be identified as a strong base, but not a very strong nucleophile. There's just too much bulk around it to make it a nucleophile. All right, that's it. So the next thing to do, I would say, is to identify leaving groups. So the very good leaving groups are those things that would take electrons with them or unshare electrons and become more stable after doing so. So the good leaving groups, we had 5 of them. We have an O+, an oxygen attached to basically a sulfate. This is kind of like sulfuric acid, but this I'm going to put as R/OH. If it's OH, it is it's just sulfuric acid. If it's an R, then it could be that S with 3 O's, SO3 attached to something. All right, so these guys are good leaving groups with those electrons, no matter what they're attached to. And then we have just kind of the standard ones that you would expect, Cl, Br, and I. All of these guys want to take their electrons and unshare them. So O from any of these directions can do that. This oxygen would have to do it that way, chlorine, bromine, and iodine. And all of these are more stable after they take those electrons back, so these are good leaving groups. Then what we want to look for is electrophiles. Electrophiles, most often, are carbons attached to those things. So a C attached to an O+. The reason for that is that the O is trying to take those electrons and leave, therefore that carbon is partially positive. and then a C attached to a chlorine, etc., etc., etc. A carbon attached to a good leaving group. There are a couple other electrophiles. One is just a straight up C+, so a carbocation, and that guy just doesn't have a full octet, so it's easy to share electrons with it. The other one that we've discussed is a carbonyl, C double bond O. And that guy, once again, it's kind of like the ones above. It's having the electrons pulled away from it, so it doesn't have enough electron density. So these are the three that you should be looking for. A straight up a C+, C double bond O, and a carbon attached to a leaving group. And in order to do that, you need to know those 5 leaving groups above. All right, so our last slide will be about acids and bases, but I'm going to put our strong acids in here. Strong acids, and these guys have a pKa of less than 0. These would be just H's attached to one of those good leaving groups. Once again, this is a very polar bond towards the leaving group. The leaving group wants to take those electrons and leave, which will leave the hydrogen all by itself. So, for example, an H attached to a chlorine, which is hydrochloric acid, and H attached to this SO4H. In all of these cases, these guys want to take those electrons and leave. Therefore, meaning that those hydrogens are going to be very removable without their electrons. These are very strong acids. Right, but we have some other acids to consider that are not strong but are reasonable acids, and that's what we'll do in the next slide. All right, so I have asked you guys to know the acids with pKa's less than or approximately less than 20. All of these guys will react with sodium hydroxide, or just OH minus. All right, so we have the strong acids that have that pKa less than 0, and then we also have carboxylic acids. These guys have a pKa of approximately 5. We have OHs that are part of either an alcohol or water. These guys have a pKa of somewhere in the range of about 16 to 18, but we'll just put 15 for the sake of making nice even numbers. And then the third one that you really need to know, or I guess the fourth one counting the strong acids, are CHs that are next to electrophiles. And the only electrophiles that we have are, these guys have a pKa usually somewhere around 20. All right, so for example, a CH right next to a CX, so halogen, bromine, whatever. These guys can be pulled off by an acid, by a base. They can grab that hydrogen and do elimination. So we've seen elimination reactions already, and the reason for that is that the leaving group is trying to leave, and one of the ways to fill the electron octet on this carbon, if that leaving group leaves, is to be able to share electrons from that neighboring CH bond. And to do that, we need to remove the hydrogen. Other examples of that include a CH just straight up next to a C+, because that's an electrophile, or a CH right next to a carbonyl. And if you look at it, these are our 3 different electrophiles that we mentioned, and the CHs next to all of those guys are acidic. All right, so that's it. I'll give you a couple examples, and please bring any questions you have to class. Thank you.